Hello, math students. My name is Tomctutor. That's my website up there, tomctutor.com. This is an extension for my advanced higher maths students primarily, but I also have to make it suitable for undergraduate students, first year undergraduate students and general engineering students studying calculus. I'm more concerned with this is the second part of a series. The first videos were to do with the differential of inverse functions, differentiation, and there we've seen that we could solve differential problems even if we didn't have the inverse function. I really want to look to the idea that we can find the integral of a function involving inverse functions as part of the solution, or the integration of inverse functions themselves specifically. Where we have the inverse function and where we don't have the inverse function. And so anyway, unfortunately I have to, because it's integration, I have to go through all the different techniques of integration here. That's what I'm going to concentrate in this video. And on the next video, I'm going to concentrate on this idea of what we call generic integration, integrate any inverse function. I must say though, for advanced higher students, they don't need to know generic integration, so they could maybe miss out completely the next video. It wouldn't hurt them. So for this video anyway, it's for specifically advanced higher students. Okay, so all that out of the way can make a start. I'm going to start with the fundamental theorem. It's the fundamental theorem of calculus, not the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is to do with prime numbers and Euclid's algorithms, etc. We're not. Okay, the fundamental theorem of calculus states that if you want to get the integral of a function, we can do that if there is a function that exists called the antiderivative. So this, what I've called big capital F here, is called the antiderivative. Derivative. Okay, we just glibly called it the integral function, okay? Can't remember that. It's usually given a capital letter representing this, the integral function of the small letter here. This f of x in here, this function, is called the integrand. The integrand in here, this f of x, is what we're actually integrating, okay? Now, fundamental theorem is quite a hefty piece of maths, so an awareness, okay? They're not going to ask you any questions about it, but I have to introduce it here so we understand it. We have it on what we call a closed interval on x, and if that's the x coordinate, then we're interested in all values of x that lie in here, including the endpoints, and that's called a closed interval. So x is a member of that set, that real set in that space, okay? And that's what we mean by the interval. Now the antiderivative will exist. We can solve this problem certainly when f is continuous, okay? And most of the functions that we're dealing with, they are continuous. It's not a problem. You don't have to worry about it, but I'm just saying that that's a fact. So if, let's assume it's a simple function, sine x or trig or exponential, so polynomials, they're all continuous. They're what we call simple functions, or any combination of simple functions. Then that will be continuous and we can always solve this problem, okay, because we can always find an antiderivative function. Antiderivative, assuming it exists, in which case here it does, or assuming it does, then its derivative will return that function. And that's why it's called the antiderivative. So we can always solve the problem, as I say. However, the function may not be continuous. And here's an example of, we have a function, so the small f here, it's a constant split on this interval. It's actually a piecewise function. But all is not lost, because we can still get the integral. We can still solve this problem even though this function has a discontinuity. So if we're coming that way, the function's got a value there. If it's going that way, it's got a function, so it's discontinuous. I think they call this type 2 discontinuity. Anyway, this is what we call a piecewise function. We can still do the Riemann sum, that is, we can still find the area under the curve. And the area under the curve will give us that solution. Now, the reason is that we've got problems with a function is it's not differentiable everywhere in the region. But that's not a problem, because, as I said, we can still find the area. We just do it piecewise. We break up the interval into two parts. We find the area there and we find the area there, and we can just add them back together. That's why. So you're quite free to split this interval up into any wee bits that you like using Riemann integration. You can do that with any function within reason. And we say then that the function is integrable. It's integrable. So we're only dealing here with simple functions or combinations of them, and we know that we'll always have a function, an antiderivative, if you like. So with that out of the way, there's some properties of functions, and what I call the linearity. I don't actually know what the property is called. Basically, it's the integral of a function that's the sum of two other functions, f1, f2 of x dx, is actually just the sum of the actual individual integrals. Maybe an x plus integral of f of 2x dx. Okay, I hope you can squeeze the way in at the end there. So, an example of that in action is if you have to integrate 1 plus x cubed over x squared dx. Okay, if you've seen that problem, you'd probably think a rational polynomial, quotient, do the partial fractions maybe, or long division or something. But no, we can use this linearity property. Linearity, by the way, because the integral of the sum of functions is the sum of the integrals. That's what I mean by linearity. So I'm going to do that here. So it's the integral of x to the minus 2, because it's 1 over x squared, plus x cubed over x squared, so that's just plus x to the power 1 dot dx. And notice that I've written this in standard form, sort of polynomial idea, x to the n, okay? So we integrate each one at x to the n plus 1 over n plus 1. So that will give us x to the minus 1 over minus 1 plus x squared over 2. So the answer to the problem is minus 1 over x plus x squared over 2. Plus, of course, the constant of integration, okay? Throughout these videos, I may miss out the constant of integration. So I do not want remarks down below saying, you have to show the constant of integration. We know it's there. It's implicitly there. Just for the sake of this series, I may ignore it. But if you're ever answering a question in any test or homework or anything, and it's ordinary integration, stick in the constant of integration. I must say that the fundamental, using what we call the definite integral, where we're solving the antiderivative between 2 points, there is no constant because it cancels either side, that's why. So we just, what this, I don't think I've explained what this means. We work out the function, we've got this interval here, and we just stick in the top interval value, b, into our antiderivative, and we just stick in the bottom value into our antiderivative and we subtract them, and we end up with a number. And the number is what we call the definite integral. Okay, it's just a number. As opposed to the integral itself, which is f of x, which is a function. And actually, to be quite precise, I should use a dummy variable here, like that. And that would, x, something like that. And that's the more sort of, I'm going way off. I didn't want to get tied up in the fundamental theorem, but we can find a function that we differentiate will give us that, then that's the antiderivative, and that is strictly a function of x. It's not a number. What could be a number? It could be a constant function. But generally it's a function containing like x as a variable. Okay, so let's forget all about the fundamental function. So the next thing I want to carry on. It's amazing how you miss wee important things out, and then it just dawns on you, you have to go back and mention them again. Sorry about that. Okay, we can integrate by inspection. By inspection, whatever that means. Well, that means basically using the tables, for instance, which you will have some basic simple function integrals in the tables in any exam or test. They're with you, they're given to you. Off the top of my head, obviously the integral of sine x is cos x and things like that. You know all that. So for instance, an example there would be the integral of sec squared x dx. Okay, now you're looking at that and you go, don't know, haven't got a clue. But when you look up the table, you'll see that that's the tangent function. Okay, plus it's constant of integration. All right, there. Okay, so just remember that. That is so. We can check that because if we differentiate there, we should get the second squared function. Okay, and there'll be exercise for yourself just to practice to see if that is the case. Okay, so fairly easy. And also, by the way, your polynomial things, the integral of x squared is obviously just x cubed over 3, etc. Alright, by inspection. Okay, right. Also just look at it. If you can see the answer, just write it down basically. Substitution, a wee bit more difficult, and there's a problem with this, but I'll show you. So let's say we have to find the integral of x over the square root of 1 minus x squared dx. Okay. Alright, now you're probably thinking, sine x squared or something like that from the tables, a wee bit of knowledge, but that's not necessarily so here. If we substitute, I'll change the colour just to emphasise the substitution. So if I put that as 1 minus x squared, if I use that variable rather than x, I can see that du is minus 2. I differentiate that, I get minus 2x over dx. Okay, so that's the differential of that down there. Okay, so that means that this du differential element is minus 2x times dx. Okay, and I'm looking at that, and I'm seeing the x and I'm seeing the dx, and I can multiply it by minus 2, and I can divide it by minus 2. Okay, so what have I got here? I have got the minus, this integral is minus a half times u itself, because that's minus 2x dx. Okay, that's for du down there. Over the square root of u. Sorry, that's du up there. Okay, which is basically just 1 dot du. Or, in terms of standard form, that's just u to the half. U to the half, okay, that's that guy. So, when we integrate that, I've got minus a half u to the 3 halves over 3, sorry, it's u to the minus a half, isn't it, because it was 1 over square root. So that becomes u to the half over a half, and that half cancels that half, and we're left with minus u to a half. Okay, and this is why I'm saying it's a constant of integration here, but I'm missing it out deliberately, okay? So it's u to a half, which, okay, so now I can go back to my x variable here. Now this guy, in terms of x up the top, which is the original problem, dx, okay, you should really call that maybe f of x to indicate that it's a integral with variable x, and this other u thing here, this u to the minus a half du, with a constant in front of it, we should write that really as f of u. These are actually the same problem, the same integral actually, but with different variables. One's a variable of x and one's a variable of u, so that's a perfectly proper notation to use. So from the substitution we go back, and we now express this in terms of x. Okay, the variable x. So we have f of x now is and what was u? It was 1 minus x squared. So it's the square root of 1 minus x squared. Okay, so what I'm saying is if you differentiate that, you get that. And you can maybe check yourself that is the case. And that's a classic sort of, that's a typical substitution type problem. So, if I may move on here, I've got to watch time, I've got to progress here. So another technique of integration, of course, is log integration. Very important, by the way, so it's very good, it comes up a lot in questions, put it that way. And what we have here, if we have a function that can be split into 2 parts, okay, so that's the whole function there, okay, and it can be represented that way, then that is equal to log n of f of x, plus of course the constant. I'll just shove it in here. Okay, so what well, why is that? Well, if I differentiate that side with respect to x, I get difference of log n of f x d f of x by the chain rule and df of x dx, and I differentiate all of that with respect to x. Remember, that's for big F, that's for antiderivative. So it means I differentiate it, I should I should end up here. Well, differential of a log with respect to its function is just d of f, so it's just 1 over f. And that, of course, is just f dash of x, which is exactly what's in there, really. So, okay. So that's the method we use. So I'll give you an example. A very good example is tan theta. I was going to say tan theta. I'll just use tan x. I don't want to confuse you. Integral of tan x is the integral of the sine of x over the cosine of x dx. So we can write that as the integral of the cosine of x prime, just like that. That's perfectly okay to do these. What that means is that's a differential. Well, there's the minus sign, isn't there? Because when I differentiate the cosine, that's what that prime means there. When I differentiate that cosine, I'm going to get minus sign. So I'll have to multiply it by minus 1 to return a plus sign, a positive sign at the numerator. Oh, now that is equal to minus the log n of cosine of x. Plus, of course, for constant. Okay, so it's a log n, log n. Alright, so apparently when you differentiate that, you get that. Actually, it can be written log n of 1 over cosine of x. Because if I take that minus 1 up there as a power, I hate writing this plus c all the time. Okay, so I'll just leave it out for the moment. And that is the log n of sec of x plus for constant, you know. What you normally do actually, you shove a constant in at the very end of the equation. It's a lot neater that way. I wouldn't worry. As long as it's in your answer. It doesn't have to be an intermediate calculations, unless you're going to actually work it out and work out its value. Okay, so that's an example like that. Okay, we'll barge on to other methods now. And another method is, where am I? Yeah, partial fractions. I won't dwell on this, okay, because it's, you know how to do partial fractions. So basically you have something like that, 1 over x squared minus 1 dx, okay? And you express that in partial, well, when you're looking at that problem, x squared minus 1, okay? You say, well, how am I going to solve that? You might be thinking about arc sines or goodness knows what, or even hyperbolic sines or something. You should see right away that that's like our quotient type thing, partial fractions. So it means it's 1 over x plus 1, I think that's a half in there, dx, plus the integral, that's not plus, it's minus, I believe. Give me a sec here. Yeah, I seem to have a half, minus a half, that's minus 1. 1 over 2 times x plus 1 dx. So all I've done is I've realised that that's 1 over x minus 1 times x plus 1. Okay, there. And I've just done the partial a b thing on that. I believe that's right. So what we now have is we can simply integrate that by inspection. It's just 1 over log n of x minus 1 log n minus a half of log n of x plus 1. That half can be taken as an index, a square root, can be taken as a square root, and that's the quotient of that over that. Subtract the logs is divide the numbers, so it's just the log n of the square root of x minus 1 over x plus 1. plus or constant. Okay. So that looks right. Okay. Check that. Right, you just check these yourself. So I won't dwell on that. That's just mainly common sense. Okay. I think I've covered them all the methods I intend to anyway. There's probably other methods, tricks, quotient rules and goodness knows what. I'm not going to bother with them. I'm just rapidly going through the toolkit that's available to you to solve problems in integration. Right, most important one now. And here I'm going to, after this, I think I'll stop this video, and because I'm going to go into this in a wee bit more depth, so I can start getting inverse, the integration of inverse functions. Okay, so this is the most important one at the moment. It's called by parts. Integrate by parts. Okay, so cut a long story short, I'll just write the definition. There's sort of many ways this is given in your course, but this is the way I am going to introduce it, because for a very special reason. That is x, f of x, minus the integral of x, f dash of x, dx. Okay, so what I've done is I've looked at this general function, whatever it is, and okay, this thing, and I've realised I can put d of x in front of it. Okay, so so that's a differential of x itself, which is obviously just 1. Okay, so you might have seen this as u dash v or something like that. And over here I'm writing that as uv minus the integral of uv dash. And this concept comes from if I differentiate both sides. And if you have an equation like this, like the integral of some function, okay, is equal to the integral of another function dy or something like that, you can differentiate both sides with respect to x. Because if the two integrals are equal, then the differential is equal. So that means that g would be equal to h dy dx or something like that. Okay, so in any event, you'd have a function here. So you can differentiate both sides. So the differentials are equal if the integrals are equal. So I can differentiate these both sides, and all I do is end up with the product rule, the duv dx, if you like, is, you can see how that returns these guys. Okay. So that's what I've done. Now I'd like you to have that from here in the next few videos on this subject, have that absolutely as the way to do it. Okay. So a quick example in the use of this. So say we have to get the integral of a log n of x of d of x. Okay. So we've got the log function, natural log function. Well, it's just simply x log n of x minus the integral of x times the differential of a log n of x, f dash of x, which is just 1 over x dx. Okay. And of course all that cancels just to give you 1. So the integral of 1 of dx is just x. So this becomes x log n of x minus 1 plus a constant, of course. So there's a typical example explaining how to do it by parts. When you're doing inverse functions, it is extremely useful. Okay, so make sure you know how to do it by parts, and all its different variations, of course, as well. you look at questions, you see things like the integral of x times the sine of x or something like that. Okay, and you can do it by parts in that as well, because we go from 1 to x here, we can go from x to x squared upon 2. Okay, and sine of x minus the integral of x squared over 2 times the cos x dx, etc. What things like that. Okay, just very rough example what I mean. So different variations of this. That's more likely the way you would see it. You would see an x in front. So if you see an x with another sort of function, by parts is the way to go. Okay. Anyway. Okay, so why is that so important to us here? Well, this is what I must produce now. What I'm going to do, that's true for any function. Okay, so any function itself. So I am going to specifically do it to the inverse function, g of x, d of x, where g of x is defined to be the inverse function of x, okay? And that is just another function, so the same by parts applies. So that becomes xgx minus integral of x g dash of x dx. Okay, now pause for a moment here. Pause for a moment. That is an inverse function. That's actually f to the minus 1 of x. That's what that is in there. So we're integrating an inverse function if we know what the inverse function is. Must emphasize. So we know what that is. We have that. Okay. So let's try a very simple example here to bring this home. Let's say we have to integrate the arc sine of x dx. We have our g of x, there it is. So that's our g of x, okay. So what is the function? What's f of x? Well, obviously, f of x is the inverse of the inverse, so that's sine of x. So, okay. But anyway, I'm specifically talking about the arc sine function. On the right hand side, that becomes x arc sine of x, because I just put g of x in there, minus the integral of x. Well, what is the differential of the arc sine? That is, what is d sine? Oh, sorry. I should write over here. What is the differential of the arc sine? Okay, I believe that would possibly be in your tables if you forget it. Okay, so it's a standard sort of thing. Well, from the first set of videos you should be able to work it out. And maybe you should do that. You should pause the video here and establish what that differential is without looking up in the table. And then check your table and see if you get the right answer. Anyway, okay, so I'll let you have a wee pause. So I'm back again, here you go. Magic of video publications. Anyway, it's 1 upon the square root of 1 minus x squared from the tables. So if I put that over here, I get the square root of 1 minus x squared dx. Okay, so we have a little integral. Of course, we solved that earlier by substitution, remember? With for u equal to 1 minus x squared sort of thing, trick in there, okay? We've done that. So what have I got at the end of the day? Yeah, so that means that my answer is x arc sine x, that's that guy come down, plus square root of 1 minus x squared plus the constant, of course, okay. Because remember that was sort of, I think that was worked out to be minus the square root of 1 minus x squared. And of course we're taking that minus, so we'll get a plus. So almost, parts. In 2 lines, we've solved a almost intractable problem using this guy. Okay, where I've substituted in the inverse function. Of course, this f can be any function. So, hopefully you see it works. But, so I've no idea how long the video's been running. I'll just introduce I'll make a start before I switch this video off on why I'm doing by parts and why I'm emphasising its importance. As you can see, it's a very powerful technique. It's a very versatile technique. And it's, you know, if you're really stuck at an integration by parts, might get you out of it. Okay, if I'm looking at this, let's take the integral, let's call this g of x, because it's the inverse function, okay? So I'll replace f with g, right? So that's g dash. Of course, that's just dg over d of x. There, right? And immediately I can cancel and end up with dg. So, just get rid of the dx. There's a bit of a mess here because I've still got an x here, and I've got my variable is dg. Let's put these in black so they're quite clear, okay? So these are functions, of course. Now, that's the first step, is to get rid of the dx, okay? Very important. X is obviously, because it's the inverse function, f of f minus 1 of x is equal to f of g of x. Of course, that is just returning x, so that is just equal to x. So that's what we have here, is x. So I'm going to replace that with this guy. Alright, that's quite important, so I'll pause and let you think about what I'm doing. I'll go over that again very carefully. I've got x here, and I realise that if I put f, the function, which is the original function, if you like, not the inverse, the function times g of x, because that is g of x, will return x, by definition. And by the way, it's also equal to g of f of x as well, because a function and its inverse are co-inverses, if you like. But anyway, that's nothing to do with this particular derivation. So what do we have now? Well, we have the final piece of our toolkit, which is that the integral of the function g with respect to x, that's g of x of course, because that's the variable, is equal to x of g. Okay. Actually, I should maybe put that x in. I'll be quite. Red pens went on me. Back to this colour. I'll write this again, sorry. Yeah. So the integral of g of x dx is x of g of x. Okay. Minus the integral of f of g dg. Now you purists out there should see there's a wee slight problem here, because the variable here is g and the variable in there is x, but don't worry about it, because at the end we just replace, put the x back in again. So treat this as a trick. Okay, this is a trick. So, forget the mathematical rigor for a minute. So, can I have I'll show you a classic problem here using this. No, I'll stop here. But this guy is what we call, it's by parts, and I call it generic integration. That is, it can be applied to any function. And you'll see in the next video why I'm calling it generic by parts. Okay, now you should be going to video 2. Thank you. Bye.